Good afternoon, everyone. My name is Kevin Letterly. I'm Government Affairs Manager with the Association of State Drinking Water Administrators, and I'll be moderating this afternoon's first half of the webinar. Thank you all for joining us. 1,400 participants, that's crazy. Good work, EPA, and appreciate you all being here. So today we'll be talking about, we'll have several presentations from several states on PFAS, but I also want to cover some upcoming webinars. On December 3rd, we'll continue with the Small Drinking Water Systems series for PFAS and lead reduction updates and lead service line identification and replacement. On October 30th, our water research theme, we have UV filters and sunscreens and impacts on aquatic organisms. On emergency response theme or research, we have November 13th, protective actions and decontamination response to a radiological event. And then under our air, climate, and energy research theme for November 19th, we have an airborne survey methane from U.S. landfills webinar. So make sure you check those out as well. Okay, so this afternoon we'll be going until 4 o'clock. We'll have 3 state presenters in the first half, so 1 to 2:30 p.m. We'll take questions after each presenter in the Q&A tab, and we'll have a 30-minute break at 2:30. Excellent. So I'd like to welcome our first presenter today, Cory Stevenson with the New Jersey Department of Environmental Protection will be presenting on PFAS treatment requirements in New Jersey. Handing over to you, Cory, to introduce yourself. Thank you so much.
Thank you very much, Kevin. Hello, everyone. My name is Cory Stevenson. I'm with the NJDEP, or New Jersey Department of Environmental Protection, where I work as an environmental engineer. Been working here for about 3 years, and I handle a lot of construction permit reviews, also work with sample plans, and also involved with a lot of rulemaking teams. Prior to working with the state, I worked in a private sector where I would run around on landfills, collect some PFAS samples, in addition to other parameters, and I also was involved in installing PFAS treatment systems in residences and small businesses. So let me get my slides up here. Okay, before we begin, let's take a brief look at the topics for today. I'm going to start with the occurrence of PFAS in New Jersey, as it helps to visualize how widespread these PFAS issues can be. We will then take a look at the 2 different treatment approval approaches in the state and the treatment technologies that have been approved for use already. From there, we will move to what our reviewers require water systems to submit in order to conduct an adequate review and the common permit deficiencies that we see. We will touch upon what our reviewers look for in terms of a pilot study in both the proposal and the results. We will close out with the current NJDEP initiatives and how they will help shape the permitting and design requirements for the future in New Jersey. In the state of New Jersey, we have 3,522 public water systems, with 1,143 of these systems being subject to the PFAS rules. On the left is a table that shows the EPA's final standards for PFAS compared to the existing New Jersey maximum contaminant levels, or MCLs. If we take a look at the table over to the right, you can see a breakdown of the current and future violations for PFAS by water system size and type. The top few rows indicate how many water systems have incurred violations for exceeding the state's MCLs since 2018. Below that are the estimated number of water systems that will exceed the EPA standards based on the data that we have for PFOA and PFOS only. At the bottom is the final estimated count of small water systems totaled up from both of the 2 sections above. We expect that a minimum 292 small water systems will need to address PFAS contamination at 354 points of entry. In total, over 30% of water systems in New Jersey will need to install PFAS treatment. Here we have some images to show the prevalence of PFAS in the state by the contaminant. The top row is the ambient surface water monitoring network, and the middle row is the state's ambient groundwater monitoring network. The darker blue and red correlate to where higher concentrations were found. In the last row is the heat map of PFAS prevalence in New Jersey water systems. As you can see, most of the contamination is in the northern part of the state and along the Delaware River. For treatment approvals, there are two processes in New Jersey that water systems can utilize. There's a normal permanent process, which is intended for water systems to submit and install permanent treatment. And we also have the temporary treatment approval process. The temporary treatment approval process is intended for water systems to use for pilot studies and interim treatment. PFAS treatment upgrades require a lot of space, which could impact the system's ability to install PFAS treatment within the state's 1-year compliance timeframe, as there might be issues with land use, backwash, waste discharge, or supply chain delays. Some water systems have proposed trailer units or other similar treatment to remove immediate exposure for their customers, while a more permanent option is designed and installed. In these circumstances, the temporary treatment approval process is the best process to utilize. The chart outlines the difference in the requirements for both the application process and the review. A temporary treatment approval is a much shorter review timeframe, requires a much smaller application package. The temporary treatment approvals, however, are only approved for 1 year, but there's not a permit application fee. For the water systems that put interim treatment into place while a more permanent measure is designed, if the system already incurred an MCL violation, they must still continue to issue public notices. So that was the application process. Now let's look at the treatment technologies that have been used in New Jersey. We've mostly seen the use of granular activated carbon, or GAC, and anion exchange resin. In other cases, we've seen some pilot studies be proposed for reverse osmosis, adsorptive medias, and electrostatic technologies, but very few of those have been approved for permanent use. One small water system proposed the use of an adsorptive media after positive pilot testing results, but its approval was conditioned in such that if it was not effective, they would switch the media to anion exchange. In general, for reverse osmosis, it is a very difficult technology to prove currently due to the highly concentrated waste stream, and there would need to be a plan to address it. If we take a look at what the NJDEP has approved already, it's a fairly even split between GAC and anion exchange. GAC dominates the higher capacity permits, while the smaller capacity permits are heavily in favor of anion exchange. In total, the NJDEP has approved 105 construction permits for PFAS at 130 points of entry. Note that this does not include modifications, and this also does not include a lot of the non-community water systems approved at the county level. Of the 105 permits approved, the work under 52 of those permits have been completed to date. Now, there are certain review criteria that our reviewers take a look at when considering a treatment technology and product. Just because anion exchange has been approved previously does not mean that all anion exchange medias work the same. And each individual product and trade name can work very different, and thus it needs to be reviewed. The first thing our reviewers consider when looking at media is, has it been approved in New Jersey before? If it has been approved before and it has been effective, then it's usually a straightforward approval with information only being requested as needed. The standard condition for approval includes point of entry monitoring that is independent of compliance monitoring. If a product being proposed has not been approved before in New Jersey, but it uses the same technology as one that has been approved, then we will likely need some more information. Typically, the reviewer will ask for case studies, such as approval in another state or use in a prior pilot study. In most scenarios, there is enough evidence there to justify an approval. In the unlikely scenario there is not, then a pilot study may be required. The standard monitoring conditions are usually extended in these type of approvals. For a new treatment technology that has not been approved before or has little track record, the treatment shall be pilot tested. These treatment technologies are when a state's temporary treatment approval program should be used. The conditions would typically require extensive monitoring and likely require the submittal of a sample plan. A quick note that there are some concerns with arsenic leaching from GAC. So all permits approved for GAC require a sample to be collected following the initial installation and all media changeouts. New Jersey's arsenic standard is 5 parts per billion, so water systems are leaning more towards using acid rinse GAC to reduce the risk. There are specific design requirements that the reviewers look for when evaluating treatment applications. The design requirements are provided in this table, and any potential deviations from these requirements would need justification. For GAC, you're looking at an empty bed contact time of 20 minutes in total with a lead lag design. This means a minimum of 2 vessels in series for redundancy. The loading rate range recommended is 2 to 8 gallons per minute per square foot. If you go below the minimum, you may see short-circuiting in your media, otherwise known as preferential pathing. If you go too high above the maximum, it can lead to issues with pressure. The media layer thickness is as required by the state's regulations. For anion exchange, the recommended empty bed contact time is 4 to 6 minutes total with lead lag design. The recommended loading rate range that you see here is manufacturer recommended, though the higher loading rate range would need to be tested as there is little data available. The media layer thickness is also the requirement under the existing state regulation. For the novel adsorptive medias, the design can vary and it is recommended to use manufacturer recommended design criteria, but also to pilot study to confirm these parameters. As previously mentioned, all media must meet the applicable certifications for use. In addition, there's a chance of bacterial growth in these media beds, which may lead to disinfection being required. The application submitted to the department must include an engineer's report and specifications. In these documents, there are certain specifications that the reviewers are looking for. If we start here on the left with the pressure vessels, we really need to know the number and dimension of the vessels. We also need to know the vessel configuration, which means that they need to be in lead lag. The flow into each vessel or train is also needed for the calculations for design, such as the empty bed contact time and loading rate. The report must include that downflow operation is utilized and a product sheet must be attached. In some scenarios, the vessels itself might not be NSF certified, but provided a coding that meets it, so that would also need to be documented. The media in each vessel is required to be outlined, including the amount of gravel. We need to know the expected pressure drop across the media. The pressure drop is important because in a lot of scenarios, a water system may need to upgrade the well pump or install a booster pump. Those are the big requirements for the vessels and media, but there are also requirements for the small features that can sometimes be omitted. At a minimum, a sample port shall be provided between each vessel to monitor for breakthrough. While this is the minimum requirement, for the large 20-foot high vessels, it is highly recommended that there are sample ports at various media depths to track breakthrough. Pressure differential monitoring is also highly preferred for the vessels. When pressure losses start to increase, it indicates that the media is either being fouled, or at least in the case of GAC, can indicate when an operational backwash may be needed. Anion exchange cannot be backwashed, so an increased pressure loss across the media can indicate that any pretreatment is insufficient. If pressure differential monitoring is not provided, then at a minimum, pressure gauges shall be provided. Pretreatment such as cartridges and bag filters are common when using anion exchange. Just because it's a minor feature does not mean its details should be omitted. All specifications shall be provided so that we can document the filter sizes and filter type. It's also highly recommended that there be some form of pressure monitoring for these filters as well. The application should fully answer some other questions, such as how much wastewater is generated and how is it handled. This includes initial rinse and operational backwash water. If it is over a certain volume, then special permitting will also apply. We need to know how long the media is estimated to last. Lab media turnaround time can sometimes take months, which introduce risks of not getting media changeouts in time. The application should also specify how and where the media is being monitored for breakthrough. If non-compliance monitoring is done to track breakthrough, we also want to know the frequency. We also want to know when and how changeouts are conducted. And last but not least, we want to know what is being done with the waste media. For example, Some systems are reactivating their GAC and getting their own media back, while others are sent in for incineration. We're going to switch gears here and discuss some common technical deficiencies that our reviewers see regarding PFAS treatment permits. These are things that can slow down the review process and otherwise cause delays with achieving compliance. The most problematic deficiencies are related to the media empty bag contact time. If the proposed design is not in accordance with the requirements, then it can lead to long delays, as to fix it would potentially require a drastic change in a treatment footprint. We also sometimes see that the volume of media in a vessel just doesn't make sense, and this is most likely due to a change during design, as installing PFAS treatment is complicated and there might be multiple changes during a design phase. Single vessel or parallel operation is also sometimes proposed without any discussion with the permitting group and with no redundancy provided. We also see treatment proposed without the proper specifications and without any information on how the media will last and how the waste is handled. So you want to be sure to include those as well. Now, those are the deficiencies specific to PFAS treatment permits. Here are a few additional deficiencies I wanted to point out. PFAS treatment is very large, and fitting the vessels and equipment inside can require full new treatment buildings. Some water systems have been using the vessels outside, and if you're doing that, it requires extensive heat tracing. And we've seen that even with heat tracing, features can still freeze and leak. In a lot of designs that we've been seeing now, water systems are using a heated valve house between the vessels, and that has had more success. So if any equipment is outside, the heat tracing efforts and all efforts to protect from freezing needs to be documented. The treatment order on drawings can also sometimes just be outright confusing. In many situations, if the system submits a flow diagram in support of the drawings, it would help eliminate a lot of the back and forth between the authority and water systems. Looking at pilot studies now, there are two routes that a system can go for pilot and treatment, and it depends on what they do with the treated water. If the treated water is put back into the water system for potable use, then the pilot study must go through the state's temporary treatment approval process. This way we can certify that all chemicals or products that are used are safe and are not introducing risk to consumers. If the pilot studies are discharging water to a sewer or being collected for off-site disposal, then no permit is required. In these scenarios, though, we highly suggest that water systems meet with the permitting team so that we can provide feedback on any parts of the study. In New Jersey, groundwater systems are not required to pilot study treatment unless it is a new media or technology. As the state is small, water quality does not differ significantly, but there's also been a lot of success in treating groundwater in all areas of the state. However, if there's a lot of iron, manganese, or competing contaminants in the water, then it might be in the system's best interest to pilot study the best treatment. We also highly recommend that surface water systems submit pilot studies, as there is very limited data out there for PFAS treatment on surface water, and water quality is variable, and it's also going to be expensive. While every pilot study proposed goes through an individual review, and the reviewers may request specific information, we do have some general guidelines for what we want to know. The table on the right is just a quick example of the absolute minimum requirements that we are looking for when reviewing a proposal. This includes initial water quality information and where the water will come from in the treatment plant. For the specific treatments, we want to know the target design parameters and flow rates. When a pilot study is complete, the expectation is that the water system shall submit a full written summary of the results with the analytical data and figures to support the findings. At a minimum, the results should show treatment removal efficiencies and the expected media or membrane life with the figures to support it. We've also had some water systems have to change out filter micron sizes to prevent media fouling during testing. So any such water quality issues during testing should also be documented. It's also highly recommended that the water systems meet with the reviewing team to discuss the results. Here's an example of how New Jersey handled a pilot study proposal. Water system reached out to discuss the idea of using a novel treatment technology that uses electrostatic treatment in conjunction with reverse osmosis. They do not have a nearby sewer, and handling waste in general would be problematic as they're a very small water system. A full-scale pilot study was proposed where the reverse osmosis concentrates the PFAS and the electrostatic treatment removes the PFAS from the water. A bench-scale study was provided to the department in addition to other case studies of its use. The department then set up a meeting with the water system, their engineers, and a manufacturer to discuss the treatment and also the design requirements that we would look for as part of the review. The application was submitted, reviewed, approved with a monitoring condition similar to that which is shown on the right here. Most of what we discussed today is more so related to groundwater design, as surface water design can be quite problematic. Groundwater applications require lead lag design and almost always use pressure vessels. This likely would not be feasible for surface water systems, especially our larger surface water systems that treat up to 200 million gallons per day at a single treatment plant. This may mean that an alternate approach to design might be needed. To adequately address and understand all challenges, the PFAS rulemaking team recently held a focus group with all New Jersey surface water systems and their engineers. The NJDEP is currently considering all feedback as we move through PFAS rulemaking. As New Jersey has prior rulemaking experience with PFAS, we've also had time to reflect on some areas that could have been improved upon. PFAS is not a drinking water initiative alone, as the installation of PFAS treatment can impact land use by requiring wetlands permits, can impact wastewater group by requiring a discharge permit for backwash water, and many other permits. A committee was formed to evaluate the full impact across the entire NJDEP. The goal of the group is to identify all permanent processes and outreach areas that can be improved. The committee includes the upper management and staff from multiple divisions at the NJDEP and representatives from both water systems and engineering firms. So that was a quick glimpse of how New Jersey handles treatment reviews, some things that our reviewers look out for, and the state's current initiatives. Thank you. I'm going to hand it back to Kevin.
Thanks so much, Cory. Great presentation. We do have some questions. Reminder, we're taking questions after each presentation. I'll take some for the remaining 6 minutes we have. So the first question, and this one has kind of two parts that I know there's another part that came in. I'll try to find. Does New Jersey only approve the use of this media vessels in a lead lag design, or do you approve use of multiple vessels in parallel?
Right now, we do require lead lag. There have been some scenarios where, due to significant space constraints on a property, where lead lag may not have been feasible, and there would need to be some level of redundancy proposed, but typically we do look for the lead lag in all applications. If there's any sort of variance there, then we would need significant justification and evidence of why the lead lag is not feasible at that facility.
Thanks, Cory. A couple more. I know you talked about your pilots. Is there a sample of one of the pilot studies available for reference?
I can speak to my management to see if we can potentially make one of those available. It also depends too on the water systems. The water systems would have to agree to any potential pilot study that they've done. They would have to agree to that being made public, but that's something I could definitely follow up on.
And another one here, how do you decide when to require post-GAC or anion exchange disinfection? Do you require 4-log chlorination? Do you require a corrosion control evaluation for GAC since it temporarily lowers pH?
Yeah, good questions. So as far as the disinfection goes, a lot of that has to do with especially any sort of extended periods of time where the media is going to sit for a while. So if you have, let's say, seasonal system, or let's say redundant filters, they would need to be accounted for in making sure that they continue to move water through them, because anytime you let them sit for too long without water flowing through them constantly, you're introducing the risk of bacteria growing on them. So I think it would be dependent on each individual system and what sort of design that they have. And in regard to the corrosion control part, that is something that we do request that all engineering firms, when they're working with water systems that are submitting these permits, they make a comment on and evaluate is the corrosion control aspect. So a lot of the permits that I've personally reviewed and seen, engineering firms are making a statement saying that long term, the corrosion control impact is there shouldn't be a corrosion control impact. A lot of the changes are going to be more short term, and that is why it's also important to follow the manufacturer's recommendations for initial rinsing procedure.
Thanks, Corey. Another question, how concrete is the regeneration of media, both process and results?
As far as GAC goes, at least from my conversations with manufacturers, um, heard that basically you're losing about 15 to 20% of the media from reactivating GAC. And that means you're adding back in 15 to 20% new media each time you reactivate. And as far as the treatment or as far as the capacity goes and treatment effectiveness for reactivated, recently held a discussion with some manufacturers, and they say in a worst case scenario, it's about like a 10 to 15% of treatment effectiveness decrease when reactivating media. And for anion exchange, to my knowledge, there is no reactivation process or regeneration process for anion exchange. So this would only be for GAC.
Thanks, Corey. I think we can do maybe one more. For our region, receiving the results of PFAS can take weeks, the soonest at 3 weeks. For some of the treatments, how can you accurately determine breakthrough when the results come so much later that a system may have been serving water with PFAS levels over the MCL for at least a couple of weeks?
Yes, and that is a big reason why the lead lag is important, because the idea behind the lead lag is that when you have breakthrough on a lead vessel, you have that immediate lag vessel right after it to protect consumers from drinking PFAS contaminated water. And it also buys the water system some time to procure that media replacement, because it's definitely understandable. It can take weeks to get the results back from the lab. And then it may also take weeks to get the media replacement scheduled and also to get them on site to actually do the media change out. So that's the idea behind having the lead lag and also taking a look at media life lifespan, because if your media lifespan is too short, then that could run into these potential issues with trying to get the media changeouts in time. So you might have to take a look at the media changeouts. You might have to add in more media, but then once you start adding more media, that means larger vessels. Might also mean that you're now increasing the other parameters. You might be having to balance everything's kind of a balance with load and rate, empty bed contact time, media lifespan, and really the lead lag design is there to try and account for those potential concerns with trying to prevent consumers from drinking PFAS contaminated water from a possible breakthrough in a lead vessel.
Great. Thanks so much, Corey. I know we have several other questions that maybe we can get to you after the webinar, but thank you so much for that excellent presentation. We appreciate that and all the work New Jersey's doing.
Thank you very much. Appreciate it.
So next, I think we're ready to pass it on to my friend Jackie Logsdon in the state of Kentucky. Jackie, thank you so much for being here. Jackie will be talking to us about the PFAS National Drinking Water regulation implementation in her state. Jackie, if you're ready to introduce yourself.
Thank you, Kevin. Um, as Kevin said, my name is Jackie Logsdon, and I'm with the Kentucky Division of Water. I've been with Kentucky for 24 years, started out as a drinking water inspector, I then moved into drinking water technical assistance. I did that for several years, and I coordinated our AWAP program for anyone on the call that's familiar with that program. And then recently I have moved on to helping with the PFAS rule implementation in Kentucky. So I'll go ahead and share my screen here. All right, so just a little bit about where we got started. We started sampling pretty early in Kentucky back in 2019. I'll get into that a little bit later in the presentation. Some other early things we started doing were engagement with water systems as far as doing presentations at trainings and conferences. We have what we call a Drinking Water Wednesday in Kentucky. We use a listserv. We use that for any drinking water related communication we want to send out. We've also been doing individual system outreach with on-site visits, phone calls, and emails. And then we also have a stakeholder committee, and I'll get into all of that a little bit as I go through the presentation. One of the things that I've noticed coming from operators in particular are a lot of questions about all of the different types of monitoring that we're talking about when it comes to PFAS. I mentioned the 2019 PFAS sampling in Kentucky. We also have had sampling efforts going on in 2023 and also through 2024, and that continues. And then, of course, we have the UCMR 5 monitoring that's going on. And then we've been talking about the PFAS rule for a while with initial monitoring and compliance monitoring. And so this graphic here just kind of has that broken out, because when we're talking about the monitoring, sometimes it could get confusing about which one we're actually talking about. There's that with the different dates that are associated with those sampling events. And then we get questions too on monitoring versus compliance. And so with this slide here, I've got it divided out in between the monitoring and the compliance determination. And with the initial and ongoing monitoring, with the initial monitoring, we'll be looking at the trigger levels that have been set in the rule. And then with the ongoing monitoring, looking at MCLs and trigger levels. With the monitoring, we're looking at each analyte for each sampling event. With the dates there, the initial monitoring needs to be completed by April of 2027. That's when the ongoing monitoring will begin. And then the monitoring and reporting violations, we're looking at those beginning with that April 2027 date. And then with the compliance determination, that is going to be looking at that MCL using the running annual average. In that running annual average calculation, zeros will be used for results below the PQL. We'll be looking at the previous 4 quarters of data, and that will only be done for the quarterly monitoring. That compliance determination begins in April of 2029. And again, that's based on a running annual average. So you have to have 4 previous quarters of data. So that data will begin with the 2028 monitoring in order to have enough to have the 4 quarters of data to calculate that running annual average. And then the MCL violations will begin with that April 2029 date. And the purpose of this slide here is just to show you that for the remainder of this presentation, I'll be focusing on initial monitoring. That's our effort right now in Kentucky, which I'm sure it is with a lot of the other states too. We've kind of got this broken down into 3 different compliance milestones. So I'm just going to focus on that initial monitoring. With the initial monitoring requirements, different data that can be used to meet the initial monitoring requirements are looking at the UCMR 5 data. In Kentucky, we have 130 community water systems that are participating that will have that UCMR data. We also have Division of Water monitoring data available for all of the water systems in Kentucky, with the exception of a few private, non-transient, non-community water systems. And then we also have water systems that have been doing their own sampling. And for any system that wants to use their own samples, we're verifying that they meet those monitoring requirements. So what we're taking a look at in Kentucky, and something that we're encouraging operators and water systems to take a look at, is what does initial monitoring look like for your system? And how does the UCMR 5 data fit in? And also in Kentucky, how does our monitoring data fit in? So these are actual monitoring dates from a couple of water systems. That top one is a system that was required to do 4 quarters of monitoring for UCMR 5. This happened to be a water system that had an issue with their 3rd quarter or their 3rd sampling event. With that 10/11/23 date. So the samples were not actually collected during that 3rd quarter. I believe they were collected and then there was an issue at the lab, and so they had to re-sample, and so that was not done until that 4th quarter date. So we went through, we put the dates in this chart to show that each quarter was represented, and then we also took into account that all samples need to be spaced out by 2 to 4 months, and we're showing a monitoring gap there with the 3rd quarter. And then when you count those months up, it's showing that this water system needs to collect a sample in August or September, which can be done in 25 or 26. And we are communicating that with the water system that they need to put that on their calendar to do that, so that they've got one sampling event for each quarter with samples spaced out 2 to 4 months. And then the example on the bottom, this is going to be a groundwater system greater than 10,000. So for UCMR 5, they only needed to collect 2 samples. But for the initial monitoring, they need to have 4 quarters of monitoring. And so this is showing that, taking into account their April 23 sampling event and their October 23 sampling event, that they need to sample in January or February, and then again in July or August. And then again, that can be done in the next couple of years. And again, this has been communicated with the water system, and we'll continue to track these as we move along. And more on the UCMR 5 data, as I've already stated in the rule, it says that UCMR 5 data can be used for initial monitoring, but as it is right now, the current reporting format is not sufficient to determine monitoring frequency, because the results below the minimum reporting level are not reported for the PFOA and the PFAS. That data needs to be reported down to at least the trigger levels to be eligible for reduced monitoring. So what we're encouraging water systems to do is to contact their lab to request the full data report. And the questions that we're telling them to ask is, what was the calibration level at the time the samples were analyzed? And if that calibration level is above 2 parts per trillion, can the sample be reprocessed? And if so, what would be the cost? We have reached out to some of the labs, and these are the questions that we're asking them as well. We are finding that some labs are going to charge for the reprocessing. It would be actually reprocessing of the data, not actually reprocessing the sample. And the cost may be high enough that the water system would be better off to resample, but that's something that water systems need to go ahead and be checking on, instead of just assuming that they're going to be able to use their UCMR 5 data. They need to be getting that answer now so that they've got time to resample if that happens to be the case. And then for the systems that are less than 10,000, since EPA is paying for those samples, they're currently working with labs to obtain this data. So next steps for water systems, this is what we're telling our systems in Kentucky, is to determine what sampling is still needed for initial monitoring. To make that chart that I showed a few slides ago, we are also sharing that with water systems so that they're aware. Again, contacting the lab for the UCMR 5 systems. And then it's really important at this point to figure out, to establish some treatment goals. So for a water system that has PFAS in their finished water, is their goal to achieve compliance and just get the results below the MCL? Do they want to treat to below trigger levels to achieve reduced monitoring? Or is their goal to meet zero, which is the maximum contaminant level goals in the rule? At that point, the system can determine if treatment is needed and then look at hiring a consultant or engineer. We have encouraged water systems to reach out to us. We are offering technical assistance in Kentucky. And so we're encouraging systems to reach out. And then systems also need to be looking at applying for funding and budgeting for installation of equipment and for future operation and maintenance of that equipment. So some activities that are ongoing in Kentucky, I mentioned the 2019 sampling event. That was not all water systems were analyzed at that time. It was just kind of a cross section of the state, looking at urban and rural, looking at groundwater and surface water. All 6 of the regulated PFAS were detected. Detections were found in both groundwater and surface water. And with those results, we are looking at less than 10% of treatment plants that potentially have PFAS above the MCL. When I say potentially, those are water systems that have had at least one result for one of the regulated PFAS to be above that MCL. We're also offering initial monitoring assistance for small water systems. So this would be small community and non-private, non-transient, non-community water systems that are less than 3,300 that are not participating in the UCMR5, and that comes out to about 63 water systems. We're on track to complete most of that by the end of this year, but some will be completed early next year. This is where we are currently with our tracking of initial monitoring progress. This is taking into account UCMR5 data and Division of Water data and some water system data. When I say we've completed, the systems have completed the initial monitoring requirements, this is with the assumption that they're going to be able to use the UCMR5 data. This is not systems that have submitted their initial monitoring package or anything like that. We don't have that full data report from labs for UCMR5. This is just going with that assumption that they're going to be able to get that data from the UCMR5. But so far, we're looking at 31% complete on initial monitoring. We're expecting 37% to finish with their UCMR5 monitoring through 2025. Another 21% will be completed through the Division of Water sampling that's being conducted, again, through next year. I've mentioned the private NCs. That's about 5% of our water systems. And then the slide that I showed earlier where there was a system that had a quarter that was not represented with UCMR5, they met the requirements of UCMR5, but there was an issue at the lab and they had to resample in a different quarter. We have about 5% of systems so far that have had an issue like that. And when we come across that, we reach out to the system to let them know that they're going to have to collect another quarter to fill that gap for the initial monitoring requirements. That totals about 205 water systems in Kentucky that will have to comply with the PFAS rule. And it's not lost on me that Kentucky is in good shape as far as the number of water systems that we're regulating for PFAS. I know a lot of states have a lot more systems than that. Some things that we are still working on, things that we still have to do. We've not developed a process for receiving the initial monitoring data yet. And we're currently working on guidance for labs and water systems to be able to submit their UCMR5 data to be uploaded to our database. Some technical assistance activities that are ongoing in Kentucky. Again, I've talked about the data tracking and the initial monitor schedule tracking. We're also conducting one-on-one site visits with water systems that may need to provide PFAS treatment. We currently have 16 water systems on this priority list. and we're providing site-specific assistance to these systems. While some of the larger systems are working independently, but we have open communication with the larger systems, so we know what they're looking at, what their plans are, and where they are in the process. And then we also have ongoing a powdered activated carbon study. So with this powdered activated carbon study, a lot of the systems on our priority list that are going to have to provide some treatment are not very high above the MCL. They might be in the 4 part per trillion range, not much above that, or they've had some results that have come back above the MCL while they've had other results that have been below the MCL. And a couple of our larger water systems in Kentucky had already started looking at powdered activated carbon for treatment. And we're seeing success with that. And so we talked to those systems and then decided to expand on that and do a study for smaller systems in Kentucky. In most cases, feeding powdered activated carbon would not require additional treatment installation, no treatment unit. I mean, it's possible that they may need to upgrade their powdered activated carbon feed system, but with the pack, it's fed into the existing treatment process. You don't need additional footprint to install large units, and it could be more affordable to operate and maintain than other treatment options. It may not be a treatment option for some of these small systems due to detention time and variability of where to feed the carbon, but that's the point of the study. And with this study, this is a collaborative effort with EPA's Office of Research and Development. 7 systems are participating, and EPA will be providing the jar testing and sampling support. The procedures will be developed based on the Kentucky studies and will be available. Those will be disseminated, and other water systems may want to look at this as well. And we have already conducted our first site visits, and bulk water and samples have been collected at these systems. We also have a stakeholder group it's a PFAS subcommittee of our water utility committee. And we have 3 subgroups: a funding, a bench and pilot study, and a communications subgroup. And this is just a really good opportunity for us to be talking to the water systems to find out what they need from us and how we can help water systems comply with the rule and provide support and resources. And I briefly want to go through some challenges that we're looking at with the implementation of the PFAS rule. Obviously, technology and cost is a big one. This is some rough numbers. This came from the EPA document on costs. And when you're looking at the estimated cost for the GAC for a 1 MGD plant installation is just above that $2 million mark, with O&M around $200,000 a year. With a 5 MGD plant, you're looking at above $6 million for infrastructure, and then around $700,000 a year for O&M. And then for a 10 MGD plant, you're looking at just over $10 million in infrastructure and greater than $1 million per year on O&M. Other challenges that we're looking at: water systems have 5 years to select treatment method and engineer a project, obtain funding, obtain approvals, acquire the equipment that may have long lead times, install or construct the project, and also collect 4 quarters of compliance data to be used for compliance determination in 2025. So actually, the first few bullets need to be completed by 2028 in order to be collecting PFAS data that's in compliance for that running annual average in 2029. There are going to be some disposal issues, looking at land farming impacts, circular liability, landfill disposal challenges, personnel. If water systems are installing new treatment technology, there's going to be training needs in Kentucky, and I'm sure nationwide. We're looking at an operator shortage. And then looking at other new and revised regulations, there's a lot on that list, and there's a lot that water systems are dealing with, and there's a lot that the primacy agencies are dealing with. And so it's, I think that this slide really puts that into perspective. So that's all I've got there. And we can answer any questions.
Great, thank you, Jackie. Yes, we do have a couple of questions. Let me pull those up. Did Kentucky have water systems submit samples using method 537.1 version 1.0? And if so, how are you addressing those? And when you consider, how are you addressing those when you consider initial monitoring? Sorry.
Okay, so right now, version 1 is not in the final rule. So currently we would not be accepting data that was analyzed under that method, and would be encouraging systems to collect additional samples.
Thanks, Jackie. A couple more. This one's about, is Kentucky requiring schools to test for PFAS while they are in session?
Okay, so that's a good question. We would be looking at the system type. So we have one school that's a non-transient, non-community, and they're a small groundwater system. So we would want to see samples collected, those 2 samples be collected preferably during the school year. We don't have a lot of schools that are water systems. We do have a couple of others. And we would be looking at wanting them to be sampled while the school is in session. Yeah, long way around there to answer that question, but yeah.
Thanks, Jackie.
Yeah.
Many of the larger municipal communities in Kentucky get their water from rivers and/or lakes and reservoirs. Are these larger communities being given a priority?
That's a really good question too. And that's true. Most of our water is surface water in Kentucky. And most of the PFAS that we're seeing are from surface water systems, but we do have some groundwater systems that are seeing impact as well. And we are prioritizing systems based on their PFAS levels. And we do have some groundwater systems that are on that list of 16. So it really depends on what the PFAS levels look like.
Thanks, Jackie. A couple more. Can you talk a little more about disposal issues? What are the current requirements for PFAS disposal?
Okay, well, we don't have any currently. And I think that that's really the difficulty right now with implementing the drinking water rule, as water systems are making these decisions on treatment, because depending upon what treatment you choose will depend upon what type of disposal you're going to need. That's something that we're looking at, but we in Kentucky do not have anything in place for disposal requirements.
Thanks, Jackie. I know that's a concern shared with majority of ASDWA's members, the state drinking water programs. What source size is being tested in your powder activated carbon study?
Okay, so we're looking out of the 7 systems. Most of the systems are less than 10,000, probably in the 5,000 to 8,000 population range, but we do have one that is greater than 10,000 in population, but it's less than 12,000, I would say. So not the teeny tiny ones, the ones that are large enough that they have like an actual treatment process to where they could feed a powdered activated carbon. So we don't have any of the really small groundwater systems that don't have actual treatment. It would be the ones that have a water plant and can have the means to feed and remove the powdered activated carbon.
Okay. Another one here. What portion of groundwater versus surface water systems had detections and need treatment for PFAS statewide?
Okay, so I would say out of the systems that have had PFAS, and the ones that are on that priority list of 16, those are the ones that had had a result above the MCL. So we had other systems that had detections, but they're lower on our list. But of those 16, I believe there's 3 or 4 that are groundwater. One has a spring source in addition to the 3 or 4 that are groundwater, and then the others would be surface water.
Great, thanks, Jackie. We may have time for one more. Let me see if I can find a quick one. Are there mobile kits to detect PFAS in water, or does it have to be done in the lab? If there is, how can such kits be made available?
I wish that's my dream, to have an easy way to check for PFAS. Right now, you have to send it to the lab and have it analyzed. And more to that I feel like that's going to make the powdered activated carbon a little bit more challenging for water systems. And that's something that we are going to be taking into consideration. With chemicals fed at a water plant, those dose rates are determined by process control testing that's done at the plant on a daily, hourly basis. And so that will be a challenge, but currently you got to collect the samples, send them to the lab, and wait on the results.
Thanks so much, Jackie. I think that's all the time we'll have for questions for your presentation, but thank you so much. Appreciate all the good work Kentucky is doing in your participation today.
Thank you.
Always good to see you.
You too, Kevin.
All right. So I think we're ready to go to our third and final state speaker for the first half before we move into our 30-minute break at 3 p.m. Eastern. So next, sorry, let me pull my, next we'll be hearing from Yasmina Markovsky with the Arizona Department of Environmental Quality on their decision trees for PFAS mitigation selection and what to do after PFAS exceedances at detection. Yasmina, whenever you're ready to introduce yourself.
Kevin, and hello everybody. So my name is Yasmina Markovsky, and I'm senior engineer with Arizona Department of Environmental Quality. I am certified a chemical engineer, but also my educational background combines polymer engineering and environmental engineering. My research focus for years was in the area of ion exchange and adsorption, which actually happened to be very handy in this PFAS era. So I'm going to share my screen now. So today I'm going to talk about decision trees and how can you use them for PFAS mitigation selection. And to use really means how to use them immediately after you get PFAS exceedances and you see that you have to deal with this issue. So I will be talking about why and how this tool was created, what kind of information you need in order to run it, and how to analyze with end goal in mind, and that way cover all non-treatment, treatment options, but also cover that simultaneous compliance. At the end, I will summarize key takeaways and talk a little bit about future ADQ steps. So how and why this tool was created? So I always like to start with problem identification, because where you have a problem, there is a need, and with defined needs, you know what has to be done. So in PFAS case, we have 2 types of support programs. We have sampling on one side, and this means UCMR5, but also Arizona has state sampling in addition to that. And on the other side, we have fundings that can help you to mitigate this issue. But question is this enough for implementation? And how you actually bridge these two? Well, when you get the PFAS exceedance, what do you do next in order to get funds and start building your mitigation? And this is exactly where we identify that the gap is. So simple manifestation of this gap is common question that we hear from public water system. And, like they get PFAS exceedance and they basically ask us, okay, now what? So this issue exists regardless of system size. So specifically in Arizona, we have 12% of public water system regulated by PFAS rule that will need mitigation. In hard numbers, that's around 115. Of those 115, 90 of them, or you can say large majority, are small, and they serve basically less than 3,300 people. And this is exactly where the gap becomes even bigger, because these small systems, they usually have limited technical, managerial, and financial capacity. Specifically for them, ADQ has a TA program, technical assistance program, but whatever we do, we really need utility to commit to those solutions. And all of this actually should not be something specific for Arizona, and probably all other states on this call are experiencing something similar. But really point here is smaller the system, bigger the issue. So that's why we decided to do this guidance, basically to help closing this gap. And this is the approach we took. So we said purpose of this guidance should be to assist public water utilities, to assist them to make decisions, to make those mitigation selections. The next one is, however, a little bit more tricky. So how to define who are you talking to? Whatever you say, there always is going to be the other side to say, but why not me? So in this case, we said we are talking to engineers who will ultimately assist those decision makers. But when I say engineers, we really think about someone with previous experience in water treatment design. So this is definitely not the area where you should start your career. This requires more. Then defining that, the next question is, how we are going to do it. What kind of guidance we are going to give, how it's going to look like, how it's going to be structured. So we said we are going to do step-by-step guidance. Step-by-step in terms of that we are going to define what information to collect, what screening tests to do, and how to select alternatives based on those information. Finally, the big question was, when is this guidance, when it should be used? And based on deficiencies and those gaps that I explained previously, we identified that we need to give something that has to be, can be used in a very early stage of planning. So that early stage means when the PFAS exceedances are detected and utilities are starting to consider compliance options and conceptual design. So to do something like this, you need a team. Now, when this document is published, I can confirm, yes, it takes a village. But that's actually the key point and value of this type of document. It is not made in vacuum. That means that stakeholders were involved from the very, very beginning. So here we had multiple people from state government, ADQ specifically. Then we had the help from federal government, specifically EPA or the office. Then we had non-profit organizations, leading media manufacturers. You can imagine, like, these are very competitive people. So how to cover it all, but not to make a conflict. And then eventually we had consulting firms, because those are the stakeholders that are eventually going to submit those applications to us. So it's very important, to be very transparent and be on the same line and have agreement between everybody. So let's talk about what information you need to run this tool. So to do any kind of design, you need information and data, and there is nothing new about that. But if you want to summarize that, I would say you need to collect knowns and screen unknowns. When it comes to knowns, that means you are opening this document because you already know that you have PFAS exceedance. But you have to say what's your treatment goal. Is it MCL? Is it non-detect? You have to be very specific. Then you have to think about other things. So it doesn't mean that you only have PFAS. So do you have any other treatment goals? Do you want to do treatment that is going to address few deficiencies at the same time or not? Then think about your water demand. What do you need? And on the other side, what do you have? What's your sources? What's your supply demand? What's your supply availability? Then how much land do you have? Footprint is very important. Then labor. You have operator, but what is his grade? What can you afford in terms of treatment? Then you will have some, you will lose some water. So how much can you afford? Then what's your corrosion potential? You should already know if you have corrosion issues in your system. And eventually, what are the options that you can afford in terms of residual management? So that's all on that known side, but still has to be defined and be very specific. On the other side, we have something that I call screen unknown. And that means that with this guidance, we said what you have to sample, where, and how often. Here we have 3 groups of analytes that ADQ is actually screening for each wellhead that has PFAS exceedance. So it may seem extensive, and some people may say, why all of this? And I will try to be very funny here and say, well, because as G.I. Joe says, now you know, and knowing is half the battle. And you will see through the presentation how it works. So let's now talk about analysis. Specifically, how to analyze with end goal in mind. I know that with this line, I'm starting to sound as a project manager, but I found it very appropriate in this case. And here is why. So end goal is very straightforward, and that's because we all want the same thing. We want to mitigate PFAS in easiest way. But when you say easiest, it's not very specific. So how you define that easiest? I think that we can say in a smart way, in a way of smart goals, which means you want to be very specific, you want to measure your results, you want to achieve your results in a realistic and timely manner. So that's why that SMART goal. And that's why we can say the goal is same for everyone, but circumstances vary and they dictate approach. And when it comes to approach, you have non-treatment options and you have treatment options. But you also have simultaneous compliance, because whatever you do, you really want to be sure that it's not on the cost of something else. So you want to be in compliance with PFAS, but also with everything else. So this is how it works. Your starting point is non-treatment, because this is usually best shot for all the systems, and especially those small and disadvantaged. I don't expect you to see all the details, but it is important to understand that these details are your solutions for specific situations. So in a nutshell, non-treatment starts with asking you about other existing sources. And this is because it's checking if you have option to switch or to blend. So if this doesn't work, then you can think about developing new source or rehabilitating the existing one. And here you have three options. I will start with the last one because that's the easiest one. And that's something that we highly recommend. That option is to connect with the neighboring system, of course. Something like that has to exist. If you are in very rural area, this may not be available. But if it is, that's definitely something that ADQ recommends. And we have been successful so far with this. Imagine it's definitely not easy to do this in Arizona. People really like water rights. But at the end of the day, when they see the cost and everything that it takes to treat for PFAS, eventually they are agreeing to connect to other systems. So start with that. Then think about new source. So if you are drilling a new well, you should be aware that this is not traditional contaminant. So you have to think about your source of contamination. You don't want to waste your money. You don't want to drill something again with the PFAS. So you have to do some kind of hydrogeologic study. You have to understand your contamination before you go and drill a new well. Eventually, you can try to rehabilitate or modify your source. And this is something that we are paying a lot of attention these days and trying to establish some kind of standard work. So basically, you have a source and you have a PFAS, and then you are checking that casing and you want to see where is your contamination coming from. So what does it take? You can start with a video recording, but it doesn't say too much. So you have to do zonal sampling, but that also doesn't have to be helpful. Then you think about dye tracing, like some new technologies. And after all, you have to be aware that this can be very tricky. May work, but doesn't have to, especially when it comes to those old wells and very small producers. Like if you have 20 GPM, you really need to know your tools, because maybe that equipment cannot even go down. Maybe, it's going to be stopped at some level. So be sure that you know what you want with this and what is available for you. So all these non-treatment options are leading to simultaneous compliance, and I will be talking later about that. And then if nothing works of this non-treatment, you should go to treatment options. So before I jump to treatment, here are just few basics that were incorporated in decision trees. First, I want to say that we intentionally focused on BAT. And that's because that's your best shot, especially if you are small and disadvantaged. I know that inventors won't be happy about this, but that's topic for something else. So in this case, I'm talking about small and disadvantaged systems, and we are leading them to BAT. Then PFAS is not traditional contaminant, so be aware that you don't want to backwash. If you don't want to backwash, then you need pre-treatment. Then it competes basically with everything that you have in your water, with TOC, with the anions, with the normal things. That affects media lifetime. Then it's trace contaminant. It can be easily pushed out. Eventually, you need lead lag, and Cory was talking about that. But if you have a lead lag, that means you need more footprint. Then the third point here that I want to say is that we don't want you to jump into piloting. This is timely and costly thing. We want you to do pilot, but don't rush with that. There is potential for big mistakes. You need this type of tools to run and to get you prepared for something like that. And eventually, don't forget about residual streams. It's very challenging. So with that in mind, we go on general treatment selection. And the purpose of this is to indicate actually potentially most suitable treatment alternatives based on more general questions. So here is what it means. you are first asked about oxidation at the source. So we have many wells with that chlorination at the wellhead. And this is because not all treatment technologies are compatible with that oxidant. Based on your answer, potential issues will be identified and options to solve then will be specified. So point of questions is not to stop you, but basically provide solutions. Tell you, hey, here might be the potential issue, but here is how you solve that. Then you will be asked about fouling, and fouling is very important. That's that pre-treatment that you probably have to include. When you think about fouling, you have to have broad view. It's about particulates, it's about organic fouling, it's about inorganic and bacterial fouling. You have to cover that all. Then treatment goals. We know you want to address PFAS, but do you have something beyond that? It's very important to know at this level. You will be asked about PFAS chain length, corrosion concerns, footprint limitations. So eventually you will end up with one or more technologies, and then you will be prompted to more specifics about each one of them. So if that's the GAC, here is decision tree. Again, you start with the fouling question. In this case, it's more specific for GAC, so it's not repeating that we had in general treatment selection. Then you have question about nitrification, and that's because if you have ammonia, then you have to deal with that. And the only way to deal with that is really to have pre-treatment. This one is very interesting. So there is always competition. You cannot avoid that, but it's very important to know how much and how much it's going to cost you. So here we are asking about TOC because TOC is major competitor for GAC. And we are asking if you have more than one. And people usually say, why one? Why not something else? Well, this one doesn't tell you stop here. If you have TOC 1 ppm, you cannot use GAC. Point is very different. It's telling you that competition starts there and that you have to pay attention. Now you need additional analysis. It's going to come at a cost. So either you are going to do the pre-treatment or your media lifetime is going to be shorter. It's really your decision, but you have to consider that. You should not be surprised eventually. So you have to calculate that. So finally, this tree is leading to treatment evaluation. And that's because this is just preliminary screening and you need to get more specific through testing. And then the next thing is simultaneous compliance, because you can put GAC, you can address PFAS, but how that affects everything downstream, that's a question to consider. So the next tree is ion exchange, and it's pretty much following similar patterns. There is question about fouling, there is question about oxidant sensitivity, because if you have oxidation before ion exchange, you're going to produce nitrosamine, and you are going to degrade your resin. And that's something definitely that you want to avoid. And this is specific for any kind of polymer-based media. Then competition. It exists here as well. It's just different type of competition. So here you're more focusing on anions. So you're talking about nitrates and sulfates mostly. Again, it's leading you to evaluate this treatment technique before you think about installation. And simultaneous compliance. And here is our third BAT, or high pressure membrane tree. So while this approach should definitely not be primary option for Arizona, there are situations where this is actually the only and best way to approach. Examples are usually complex water matrices with extreme salinity and multiple treatment goals. And we do have these. Water in Arizona has high salinity. So what is specific for membranes? Again, you are checking about fouling, but because with membranes, you have those high recovery processes, you are recycling streams. So it's very important to address all of these in your raw water, but also in the stream that you are going to recycle. So it's more into that. And then when it comes to that pre-treatment, in this case, it's not kind of choice. It's not part of optimization. It's more like necessity, because if you don't have pre-treatment with the membranes, you can get very extreme equipment failures. Then you will be asked about oxidants, because we are talking about polymer membrane, so you want to eliminate that before the contact happens. And then eventually waste stream considerations. So you can even, address this with that screening knowns, because if you know that you don't have option for waste stream, then you should not be actually looking at this three. Waste stream is major issue with the membrane. What we know is that nanofiltration is making less waste, and it's effective for PFAS. But it is interesting that I am not aware of any system using nanofiltration to address PFAS. So please, if you know some, let me know. I would like to learn more and understand why we don't see more of these. Again, whatever you do here, it will lead you to simultaneous compliance. And here we are, simultaneous compliance. That's last decision tree. Here is official definition, but I like to say, it really means whatever you do, don't mess up with something else. You solve one thing, but you don't want to open another issue. And in this case, we are focusing here on corrosion control and bacterial control. And I think that previous speakers also spoke about this, but the point is that you are here either changing source or treatment. And whenever any of these happen, you have to go and do corrosion control evaluation and basically address your OCCT, optimal corrosion control treatment. You have to reassess that. And then we have bacterial control, because all of a sudden you have a filter. That water is going to be stagnant there, maybe for days, maybe for hours. It really depends. It depends on temperature. It depends on many things. What the impact is going to be. So we have water stagnation, and then we have potential fines in your effluent. So all of this it's going to support bacteria growth. So we highly recommend chlorination to come after any kind of treatment. And here is simultaneous compliance 3. You can see the difference is made between non-treatment and treatment options. They are both leading to corrosion evaluation. And then you will have situation treatment going to post-treatment disinfection, which eventually, again, can lead to corrosion control evaluation, because if you didn't have any chlorination before, all of a sudden you are putting that, so you are changing your oxidation potential of water, which means you have to address that corrosion. So let's see, I will go quickly through some key takeaways. What can I say? Selection is utility specific. There is many factors to consider, and it's more than media lifetime. Non-treatment is just starting point, and it should be priority for small systems. Treatment is not easy, but you can achieve that. It is important to think about pre-treatment. That's going to basically support your treatment, whatever you decide. Technology evaluation is critical, and it comes after decision trees. collaboration is very important. What does it mean? It means that we want clear expectations from utility. They have to say what they want. They have to involve engineer from the very beginning. They are vendors. Many of them are providing support. And that's something that is great. We should use that. And then eventually, when it comes to regulator, we have to come with transparent expectations, because it's much easier to communicate that way. Then number 6 says examination is cheapest way. It really means spend now and save later. Spend on this screening. It will help you to get your decision. Don't forget about cost analysis. All of this is technical, but eventually it's techno-economic decision. And then permitting, it can be straightforward. So if you follow recommendations and communicate in an open way, it can be easy process for both sides. If you didn't so far, you can get your copy now. I don't think that I can spend too much time on this. I'm running out here, but you can find it online as well. And then we are really hoping that this is not last document that is coming as a support from ADQ. We are working on testing protocols, but in a very different way. So beyond the pilot testing, there are bench scale testing that can supplement and work together with these pilots. And then if you also involve modeling, you can get things in a much faster way. So we are focusing on kind of accelerated type of testing that maybe requires you to approach from many sides, but eventually get your testing results in a short and cheaper way. Then point of use, point of entry considerations. This is a tricky part. So we are trying to help our customers and say, when is yes, when is no, and how to do it. Cost tools, we cannot do any of these without knowing how to calculate cost. And then eventually waste management options. Other people mentioned it's really elephant in the room. So we have to say specifically, define what is requirement from ADQ, and then keep adjusting that in line with the upcoming regulations. Be free to contact me anytime, but just to know, beyond me, there is entire ADQ team working on PFAS. So in case that you have other than technical questions, please contact my colleague, Sarah, which is our amazing PFAS project manager, and she absolutely helped Decision Tree project get realized. Thank you.
Thanks, Yasmina. We will do a couple of questions before we move into our break. With TOC competition for PFAS treatment with GAC, is the issue that high TOC levels will cause the media to be exhausted faster and require a higher media changeout frequency?
Yeah, that's correct. That's how any kind of competition works. So it's fighting for the same site, your media life is going to be shorter. It doesn't mean that it's not going to work for you, but it's important to know what that short is. How much is that? How often you will have to change your media? How much is that going to cost? And then eventually, is your TOC on the same level all the time, or it's going up and down? What are those variations? Is there seasonal impact? So that's why all of this sampling is important. We know that TOC has impact, but it is about TOC, it's about concentration. And it's about ratio of TOC to PFAS and everything else, all the other background interferences.
And a similar question, Yasmina, what other contaminants should we be concerned about for competition for PFAS removal with GAC? Is the issue also with faster media exhaustion or something different?
So we were very specific about this in this document, so you can find all the details there, and that's why that extensive list of what you have to sample for. But I would say if it comes to GAC, then your competition is those organic. So it's TOC mainly because it's ppm level. But it's not only that, it's all the group of SOCs, or full group of VOCs. So all them are competing, but we really stress around TOCs because TOC is ppm level. So imagine that ppm over ppt, those orders of magnitude, it's really winning the battle. So VOC, you can expect much lower concentration. So it's going to cause competition, but not that much. So it's not only TOC, but TOC has highest impact because of concentration.
Thanks, Yasmina. Two more questions and we'll go to break. Why is backwashing not recommended for GAC filters?
So this is something that is very commonly asked. I know that many other states say don't do it for ion exchange, but you can do it for GAC. We are not recommending this to be done for any kind of media because really background of this is when you are doing backwash, you are disturbing your mass transfer zone. And people say, yeah, but I did that before and nothing happened. Well, before is before. That was conventional contaminants. Now you have PFAS. It's so low that PFAS, that whatever you do, it has huge impact. So forget about all the previous, practices and everything. Here you are disturbing things and you will see impact. If you have to do it, you will do it. I mean, if there is no other choice. And that impact is going to be smaller with GAC because you have different granular size. It's going to re-stratify, not in an ideal way, but it's going to have some order. If you do that with ion exchange, it's going to mess up everything. So definitely, we say if you can avoid backwashing in any way with any media, you will have benefits. The only way to do that is with pre-treatment. But if you have to do it, then do it slowly, do that backwashing, because probably that's the moment when you don't have anything else to lose. Because if that backwashing doesn't work, you will have to change your media. I know that some systems were taking like an initial layer of media because they had that fouling issue. But that means that you are sure that your pressure drop is on the top of your vessel. So you can remove that. So some people are doing that instead of even trying to backwash. Again, it's all about optimization. So if you ask me, whoever does ask me, should I backwash? I would say no. Try to avoid that. But if there is no other option, yes, but watch out, there will be a consequence.
Thanks, Yasmina. Last one really quick, and then we will go to break. What's your thought of having a lead vessel of GAC and a lag vessel of resin?
That's a very interesting one. And I think that there are specific situations that really require that. It can be that lead lag, or it can be, maybe it can be 3 vessels. So let's say that you have PFAS and nitrate. So you want to split those two because nitrate requires regeneration. PFAS cannot afford that. So in those situations, I usually recommend go with the GAC first, remove that PFAS. Nitrate will pass through, and then put ion exchange for nitrate, and then be sure that PFAS is not coming to ion exchange. So be sure that you have that good media, GAC, taking that PFAS. So you have only nitrate on ion exchange, so you can regenerate that ion exchange and not having PFAS in your waste stream. So it definitely is good approach for some situations, but it requires more O&M skills and overall more activities.
Thanks so much, Yasmina, and thank you to all the state presentations this afternoon. We're now on a 30-minute break, and we will resume at 3 p.m. Eastern Time with some additional presentations. So thank you all so much, and we'll see you very soon.
Thanks, everyone, for sticking around. So we're now starting the second half of today's extended webinar. So yeah, great first few state presentations. Now we're excited to hear from a couple of folks at EPA's Office of Research and Development. So yeah, it's now my pleasure to introduce our first speaker, who is Samantha Smith. She is a physical scientist at EPA's Office of Research and Development, Center for Environmental Solutions and Emergency Response, Water Infrastructure Division. She has supported EPA research in various roles since 2004, in laboratory and field studies covering diverse topics impacting water quality. She holds an MS in environmental science and recently completed her PhD in environmental science at the University of Cincinnati's College of Engineering and Applied Science. Her current research focuses on PFAS removal from drinking water matrices using an ion exchange resin. So, with that, I will now turn it over to Samantha.
Thank you, Drew. I will be sharing my slides now. Please, getting back here. Okay, so this audience is likely already familiar with PFAS and why PFAS contamination is a concern, as well as that recently finalized national primary drinking water regulation for the 6 PFAS listed on this slide. So based on the PFAS occurrence in finished drinking water that was observed during the 3rd and 5th UCMR sampling programs, many utilities in the US will need additional treatment to meet those final MCLs of the PFAS rule. Anion exchange resins are one treatment technology that has demonstrated success in PFAS removal. And just to visualize how that anion exchange process works, on the right is a representation of a resin bead. The resin consists of a polymer, typically polystyrene or polyacrylate, and the strands are bound together to form a mesh-like matrix. On that matrix are positively charged functional group signs, which are shown as the blue plus sites, which are shown as the blue plus signs. And those are initially loaded with a counter ion, such as chloride, which are depicted as the red minus signs. So during water treatment, other anions, for example, a contaminant like PFAS or inorganic anions, those are represented by the green minus signs. And you can see on the left side of that figure an example of how it would exchange with the chloride. So that anion would then occupy the site and the chloride gets released into solution. And while anion exchange is promising for PFAS removal, we need more information for treatment optimization. And there are several approaches to investigating anion exchange treatment. Pilot studies are frequently used for estimating the efficacy of full-scale treatment, but they're costly and time-consuming. The results are limited to the study design and influent conditions, and it's really not practical to run a pilot for every specific treatment scenario. Laboratory studies are also common, but for PFAS, there are limited data and widespread errors pertaining to isotherms and kinetic models. And also useful information is often omitted, such as the effects of major competing inorganic anions, which also occur in drinking water. Lastly, treatment models are useful tools that can help us design effective pilots, understand our results, predict filter changeout, and also understand cost drivers in treatment systems. And if you'll be tuning in for the next talk, you'll also learn about a lot about EPA's PFAS modeling efforts from John Burkhart. Specifically related to this research, an ion exchange column model was recently developed by US EPA, and that's publicly available at the GitHub link at the bottom of the slide. Just to quickly summarize, this model is capable of handling monovalent and divalent ions in drinking water, including PFAS. It uses the homogeneous surface diffusion model, or HSDM, for gel resins, and the pore and surface diffusion model, or PSDM, for macroporous resins. And column performance is typically assessed from breakthrough curves. And here you can see an example plot of nitrate breakthrough from an ion exchange column. The plot shows influent normalized effluent data, or C over C naught, versus bed volumes, with the pilot data as points and model simulation as lines. You can see in this example that the model's done a really good job here. However, to support further model development, we need more data. And there are several research gaps that must be addressed to better understand PFAS treatment via anion exchange overall, and also to support that ion exchange column model development. First, the empirical models that are commonly used don't provide much insight, and the fundamental parameters needed by mechanistic models are scarcely reported, including the equilibrium and kinetics parameters. Also, few studies are conducted at conditions relevant to drinking water. Many instead focus on highly contaminated sites or other environmental matrices. And PFAS studies also often don't address major inorganic anions that are present in drinking water, such as nitrate, sulfate, and bicarbonate. And these are important to include because they're usually at concentrations orders of magnitude greater than PFAS, so milligrams per liter versus nanograms per liter perhaps. And these can compete for exchange sites rather, leading to increased resin usage. And secondary to this, the relative changes among concentrations of the inorganics themselves during anion exchange treatment, this could create concerns regarding corrosion control. So it's not only essential to investigate them in relation to PFAS treatment, but also pertaining to anion exchange usage in general. Lastly, the impacts of natural organic matter or NOM on PFAS treatment by anion exchange are still poorly understood. Of particular relevance to this research, NOM can inhibit contaminant removal by anion exchange, either due to direct competition for those exchange sites or by physically fouling the resin surface, which would block access to those exchange sites. Therefore, to address these gaps, we conducted pilot scale anion exchange column studies focused on obtaining values for the model input parameters, getting column breakthrough data sets for PFAS and inorganic anions at drinking water relevant conditions, and also assessing NOM effects. Just briefly covering some overarching materials and methods for these column studies. The anion exchange resin that was used in all of the columns experiments was the Purolite PFA 694E, which is a strong base polystyrene divinyl benzene resin. It is gel type, so it does not have macropores. It comes in the chloride form, and we rinse and condition that before use, and it is intended as a single use resin, and it is PFAS selective. The NOM treatments used NOM that was sourced from concentrated lyophilized Ohio River water that was produced in a previous study. We reconstituted that into stock solutions, which were used to dose our column feed water. And this helped produce realistic, stable influent conditions in our lab-created source water. For PFAS, the 9 compounds listed here were included. This was based on toxicity assessments by US EPA that were available back when we started this research around 2018. And these also include the 6 that are in the PFAS role. In summary, there are 5 carboxylic acids or PFCAs, 3 sulfonic acids or PFSAs, plus 1 ether acid whose name is GenX. And among these PFAS, the carbon chain lengths range from C4 to C10. The major inorganic anions, I'm abbreviating that IAs, these were chloride, nitrate, sulfate, and bicarbonate that we included in that feed water. Samples that we collected during the studies were measured for this list of analytes. The PFAS analysis followed an established LC-MS-MS online SPE method. Inorganics were by ion chromatography. Bicarbonate concentrations were calculated from total inorganic carbon and pH. We also measured pH and temperature, and the NOM parameters included TOC, UV absorbance at 254, and those combined as SUVA or specific UV absorbance. And for the column systems themselves, here's a schematic of a column train. 4 of these systems were built for this research, and they were constructed to completely avoid PFAS containing materials, which was no small feat. The flow path is shown left to right. Each system is fed from a 200-gallon HDPE feed tank using an HPLC extraction pump, which is set at 40 mils per minute. A pre-column with silanized glass wool precedes the resin columns to protect from fouling. And then 2 1-inch diameter resin columns are plumbed in lead lag configuration to allow for sampling of 2 empty bed contact times or EBCTs from each system. And again, these are pilot scale experiments, so we're using full-size PFA 694E resin, and all treatments were conducted in duplicate systems. So we started off with a column study that focused just on the inorganic anions before we jumped into PFAS. And the EBCTs for the inorganic study were 2 and 4 minutes. The feed water was prepared from distilled water, and experiments were run at 3 different concentration conditions, low, medium, and high for those inorganics at the ranges given on the slide. And the feed was prepared using all of the anions together and then adjusted to pH 7. And a separate experiment was also conducted at that medium condition, but with the addition of NOM, and the target NOM concentration was 2 milligrams C per liter. So from the columns experiments for the inorganics, we can generate breakthrough curves, which is again C over C naught versus bed volumes. And the anion series I've color coded with experimental data as points and the model simulated data as lines. This figure is an example from the 2-minute EBCT with the medium concentration inorganics without NOM. And you can see breakthrough occurs very quickly for the inorganics over the course of hours to days, and we observed little to no NOM impact. The order of breakthrough was bicarbonate, which is in blue, then sulfate, which is in pink, followed by nitrate in orange. And this follows the expected order of evolution based on their selectivity values, and that's just their affinity for the resin relative to that of chloride. And this just demonstrates that the least selective anions will break through first. The curve for chloride in green, you can see moves in the opposite direction of the other anion curves because that's the initial counter ion loaded on the resin, and it's being exchanged off as the other anions exchange on. So overall, there was good model agreement, including capturing that chromatographic roll-off where bicarbonate and sulfate exceeded their influent concentrations. That's where they are greater than C over C naught of 1. And lastly, as expected, water quality changes did occur during anion exchange treatment, including a period of decreased pH, which was during bicarbonate removal, as well as some changes in their relative concentrations, such as simultaneous sulfate removal and chloride release. And these parameters in particular could affect corrosion control. So to look more at the utility of the model in evaluating these effects, we simulated some practical scenarios with the ion exchange column model, including initial startup of new resin, and an abrupt change in source water. And to briefly summarize, those water quality effects were short-lived, again on the order of hours to days, compared to the timeline of expected PFAS breakthrough, which would be months to years. So the impact to operations should be minimal and could possibly be mitigated by measures such as wasting your treated effluent, blending, or staggering change out of resin contactors. So next we moved on to experiments to evaluate PFAS breakthrough, and this was using the same pilot scale column systems and full-size PFA 694E resin. Conditions with and without NOM were run in duplicate for each of these experiments, and the feed water conditions were similar to the medium concentration condition from the inorganics, plus the addition of 9 PFAS compounds with each of those PFAS targeting 500 nanograms per liter in the influent. And as with the inorganics, the feed water was adjusted to pH 7, and we did our sampling design for collection times based on ion exchange column model simulations for the experimental conditions. The PFAS experiments were conducted over, 2 experiments, and that covered 4 different EBCTs. First, that top experiment used shorter beds, 0.5 and 1 minute EBCTs, and this was to observe breakthrough for as many of the PFAS as possible, which is challenging due to their wide range and selectivities. So the second experiment then used longer beds, the 1.5 and 2.5 minute EBCTs, and this was to better capture the breakthrough of the 3 least selective PFAS, which elute the fastest. Those were PFBA Gen X and PFHXA, and would also allow us to get better resolution on any NOM effects that had occurred on those. All other conditions remained the same between the 2 experiments. And while the inorganics experiments ran for 7 days, you can see that the PFAS runtimes are much longer here, 9 months and 13 months for those 2 experiments. So just briefly looking at the non-PFAS constituent breakthrough behavior, the inorganic anions breakthrough, which isn't pictured, that concluded by about 500 bed volumes. So that was very quickly and similar to what was observed in the inorganics experiments. The breakthrough for the non-parameters is shown in this figure. Going top to bottom are SUVA, then TOC, then UVA 254. And based on these, non-breakthrough had concluded by about 50,000 bed volumes. And beyond this relatively short breakthrough period, you can see that the influents are very stable. And this is particularly beneficial for model validation purposes, as opposed to a natural water with fluctuations in natural organic matter content. So just to show some overall trends, here are the breakthrough curves for all 9 of the PFAS with panels for each PFAS as columns, and these are for the 0.5 and 1 minute EBCTs. I'm focusing on those just because they have more PFAS breakthrough data. The breakthrough trends largely related to PFAS selectivities from the literature, and they varied by chain length and functional group. For the carboxylic acids, which I'm outlining in orange, you can see increasing removal or less breakthrough as you move from left to right with increasing chain length. So PFBA on the left is a C4, PFDA on the right is a C10. Similarly, for the sulfonic acids in green, we see increasing removal going from PFBS, which is a C4, to PFOS, which is a C8. And comparing these two groups, we see the sulfonic acids have much better removal than the carboxylic acids of the same chain length, which is expected due to their much higher selectivities. And I'll come back to GenX breakthrough behavior later because there are some interesting things happening there. And lastly, looking at NOM effects overall, you can see that the treatments with NOM, which are in red, tend to break through earlier than those without NOM in blue, meaning that the NOM is causing some reduced treatment performance. And there are some obvious differences in the magnitude of this effect among the PFAS. So looking at the effects of NOM on PFAS breakthrough, we observed that NOM effects varied by PFAS and by EBCT, and this was apparently due to physical fouling of the resin. And it was useful to make comparisons based on early breakthrough simply due to having more data among the PFAS. Early breakthrough, I specifically mean BV10, which is bed volumes to 10% breakthrough. And this figure shows the percent change in BV10 for treatments with NOM versus without NOM, where there was sufficient breakthrough data to do so. So the trends among PFAS largely corresponded to selectivity, and minimal NOM effects were observed for the less selective PFAS. For example, PFBA only saw a 2.8% reduction in BV10 versus a 74% reduction for PFDA. An exception to this was PFBS, and based on its selectivity, it was expected to trend somewhere between PFOA and PFNA. However, it had later breakthrough, so greater removal, and also lower NOM effects than expected. And both of these could be explained by PFBS's smaller size. Its molecular weight is lower than the other very selective PFAS, so it could be expected to have much faster mass transfer kinetics, as well as be able to get in and access sites that the larger PFAS couldn't reach. And this would result in its lower NOM effects compared to similarly selective PFAS. Also, PFNA and PFDA had similar NOM effects despite an order of magnitude difference in their selectivities. And this is likely because the resin was already fully saturated with NOM during the early breakthrough period of these later eluting PFAS. And lastly, there were some possible kinetic differences between PFHXA and GenX. And these are both C6 chain length with similar selectivities, but they have different structures. And the NOM effects increased for PFHXA with increasing EBCT, but the opposite was true for GenX. So digging more into GenX specifically, I've alluded to some unexpected GenX behavior. Here are the breakthrough curves for GenX, and you can see that GenX's effluent concentrations plateaued below the influent concentrations, which I've given as the dotted line at C over C naught equals 1. The starting points of this plateau varied with EBCT, as shown on the figure, with decreasing bed volumes to the start of the plateau as EBCT increased. And this trend points to something other than typical adsorption being the cause. So there are several reasons that this was judged to be a legitimate effect. First, these trends we've observed were among all of our conditions across 2 experiments and in duplicate treatments. Second, only GenX behaved this way, yet it was dosed, collected, and analyzed simultaneously along with the other 8 PFAS. And third, the plateau lasted a very long time with no observable increase in C over C naught. For example, even on the longest bed, which was that 2.5 minute EBCT, it ran for 75,000 bed volumes and additional breakthrough was not observed. So to further assess this, the plot here shows the mean value of the breakthrough plateau on the y-axis versus EBCT. Conditions with NOM are in red and without NOM are in blue. The plateau values were lower with increasing EBCT and were also lower for conditions without NOM compared to those with NOM. So it appears that GenX is being transformed or degraded while in contact with the resin. GenX, which is an ether, has an oxygen atom in its carbon chain, and this has been shown to be a weak point for chemical or biological degradation. However, in this study, we used much shorter contact times and lower concentrations than literature studies that had demonstrated this. So more investigations needed to explain why this would have occurred in our systems. So we did some preliminary non-targeted analysis to look for possible GenX degradation products in the influence, but none have been observed so far, so it remains an area of future study. And interestingly, this GenX behavior hasn't been reported in previous pilot studies, likely because their runtimes were shorter than when this effect would have become observable. And because of the effect of contact time, rapid small-scale column tests or RSSCTs would be even less likely to observe this effect. So getting back to the PFAS experiments as a whole, the ion exchange column model was applied to simulate column effluent concentrations and to evaluate model performance in comparison with those experiment results. And here's the list of model input parameters. I'm not going to cover these individually, but we got everything either through previously reported data or they were obtained earlier in this research, or we calculated them from experiment knowns with 3 exceptions. First, the liquid film mass transfer coefficient, or KL, was estimated from a commonly used correlation, and selectivity with respect to chloride and interparticle diffusion coefficient. These were estimated by fitting the model simulations to the breakthrough data. So some lessons learned from fitting these parameters were that we really need to hone in on getting more accurate DS estimates, that's that interparticle diffusion, and a direct measurement method is desirable. We need to track resin materials closely because there were some significant differences that we observed between lots. And also selectivity and capacity are interrelated. So it would be helpful to devise a way to get PFAS specific capacity values and disentangle those parameters a bit. So in order to have enough data to fit the selectivities and interparticle diffusion coefficients, the PFAS needed to hit at least 50% breakthrough. And with this constraint, column model simulations were able to be performed for 6 of the PFAS. And this included PFBA, PFHXA, and GenX at all of the contact times, and PFOA, PFNA, and PFBS for at least 1 contact time. PFBA was overall well described in all conditions, and for this and subsequent plots, all the points are the pilot data and lines are from the model simulations. PFHXA also showed good model fit with the exception of some chromatographic overshoot. Again, that's where the effluent concentration exceeds the influent concentration. This occurred on the longer beds, both with and without NOM, and couldn't be captured through various changes in our model inputs or competition among PFAS. So some underlying assumptions in the model should be reassessed. And of course, because of the non-adsorption removal of GenX previously discussed, the column model can't be expected to explain that GenX breakthrough. Next, PFOA was well described by the model, except for some incipient breakthrough that was not observed experimentally. PFNA showed that the model correctly predicted the extent of breakthrough, but the shape of that curve was poorly described, including some incipient breakthrough here as well. So for both of these, they appear to have been affected by overestimated film transfer coefficients, or KL, from that correlation. So we're looking into some alternative correlations currently. Lastly, PFBS was well described by the model for the conditions with available data, and the evaluation of the model performance versus the pilot study data was very useful to better understand PFAS and an exchange behavior and to illuminate some of those areas for improvement in further model development. So just to summarize some of our conclusions, from the inorganic study, we saw that the elution from columns occurred in the order of increasing selectivity of the inorganic anions, as one would expect. The NOM had minimal effect on inorganic anion breakthrough, and while some water quality effects related to corrosion parameters were observed, these were short-lived. Lastly, the column model was validated for the inorganic anions. From the PFAS study, PFAS breakthrough largely trended as expected based on chain length, functional group, and usually by their selectivities. NOM caused earlier breakthrough, with the effect varying among the PFAS, usually with later eluting PFAS having a greater NOM effect, and this was apparently due to physical fouling of the resin. GenX breakthrough behaved anomalously, plateauing at less than its influent concentration, which points to transformation or degradation occurring within the resin columns. And tracking of resin lots is recommended based on some observed differences in resin parameters and treatment performance in this study, as well as in comparison with previous studies. And there's a need for better estimates of diffusion parameters, in particular, a direct estimation of DS and better correlations for KL. And lastly, for conditions with available data, the column model successfully simulated PFAS breakthrough with a few exceptions, that chromatographic overshoot on PFHXA, the incipient breakthrough on PFOA and PFNA related to that KL, and the non-adsorption removal of GenX. So overall, the results of this research provide us with essential information pertaining to anion exchange treatment of PFAS in drinking water. And to continue from here, some future recommendations would include continuing to investigate several model parameters. The PFAS interparticle diffusion estimates, or DS, are currently being investigated using centrifugal stir devices shown in the photos. We're also looking into improving film diffusion estimates and potentially a PFAS-specific exchange capacity method. Several efforts could help us better understand NOM impacts. We already have multiple studies using macroporous resins underway, including some pilot scale columns. Future experiments could also investigate preloaded resins, obtain equilibrium and kinetic parameters for the NOM itself, and the column model should be updated to account for these effects. And additional PFAS breakthrough data would be helpful, especially for the later eluting PFAS. However, this requires long run times and a lot of resources. Rapid small-scale column tests, or RSSETs, have been used for GAC for decades, but more fundamental work is needed for the anion exchange scaling equations, since they're expected to differ from those used for GAC. Lastly, for the non-adsorptive removal of GenX, a few things that may help reveal a cause are continuing non-targeted analysis of the column effluents and the spent resins, and we could also get more data from running at longer EPCTs. Here are my references for the presentation, and thank you for attending my talk today. Please feel free to reach out to me, and I'll also point you to Levi Halpert for questions on the anion exchange modeling.
Great. Thank you so much, Samantha. Great presentation. Do have time for a few questions. So first off, did you see effects from the grain size of the medium, speaking of full size, relative to the column scale of the tests?
I'm sorry, can you repeat that question?
Sure, yeah. So did you see effects from the grain size of the medium, full size, relative to the column scale of the tests that you conducted?
So I'm not exactly sure what the person asking the question is going for. We did not look at different particle sizes. We looked only at the bulk size of the resin, but the size of the resin in ratio to the diameter of the column is about 1 to 40, which is a large enough ratio per the literature to avoid effects of channeling down the column walls and short circuiting. So I hope I answered that question.
Thanks, Samantha. So next, what is the number of bed volumes for effluent concentration to reach PFAS MCL?
So that depends on the PFAS. So for PFOS, for instance, it's a very selective PFAS compound, and we did not see it exceed the MCL during the course of these 9-month and 13-month pilot studies. So that answer varies based on the other PFAS as well.
Thanks, Samantha. And let's just do one more question. Would your measured Ds and KL parameters be available to the public?
So our specific values, yes, I have a publication in preparation right now. Hopefully that will come out in the coming months or maybe next year. It's in my dissertation. So that correlation, however, is in the ETDOT manual and the Nielinsky correlation. So if you're familiar with ad designs, you can look in that manual and find that correlation there.
Very good. Well, thank you, Samantha, so much. We'll now switch over to our final presentation of today. Jonathan, if you want to start sharing your screens, and I'll quickly give you kind of an introduction here. But anyway, so Jonathan Burkhart also is with EPA's Office of Research and Development. He's an environmental engineer working within their Center for Environmental Solutions and Emergency Response, Water Infrastructure Division. He has over 10 years of experience in research associated with drinking water quality and supply topics. Jonathan is currently leading research into modeling PFAS removal using granular activated carbon and ion exchange systems, and modeling water quality in premise plumbing systems and water distribution systems. Jonathan holds a PhD and MS and a BS in chemical engineering from the University of Cincinnati. So with that, Jonathan, I'll turn it over to you for our last presentation to close us out today.
All right, thank you. I get to the pleasure of closing this out, and there's been some really good topics so far, and so I get to actually highlight some key aspects. But I'll be talking about the open source or free treatment performance modeling tools that EPA is making available. Similar to Sam, I'd like to acknowledge both my co-authors, but also just the team behind that. And you can see a fairly large list of people producing great information that feeds into these modeling efforts. So drinking water treatment, goes beyond just the drinking water utility and that's topics of reactivation, landfill, and whatnot. But this talk is really just focused on models that support the drinking water utility, the treatment scale work there. And again, there's a lot of people that at EPA and elsewhere that are looking into some of these other topics. And so be on the lookout for information about all of these topics. So the previous talks have really highlighted these technologies. So I just want to sort of focus on the topic of the top two technologies are carbon and resins. They've been described in great detail by previous speakers, but they have the breakthrough behaviors. So they can remove, essentially 100% of the contaminants for a time. And so we'll, sort of touch on that. But generally, they can, all the technologies, including the high pressure membranes that have also been discussed previously, can remove co-contaminants, although the types and specific co-contaminants may vary, and they can have other, positive benefits to your treatment train that you can, look into if you would like. But there's also issues, and that's also been discussed. And so the idea of unintended consequences or the impact on other types of compliance with other regulations. Sam talked about the increase in chloride to sulfate mass ratio, which could potentially lead to corrosion. That with resins, the topic of carbon potentially impacting arsenic for the initial flushed water was brought up as well. But for the purpose of this discussion, we have potential overshoot. Sam talked about that, chromatographic roll-off. Some of the short chain compounds can be difficult to treat, so understanding if that is a concern for your system, you can think about that, and that's where models can potentially help you with that. But we'll talk more about the idea of the reactivation or disposal cycle. So that was really discussed in previous talks. So how frequently are you replacing the media for those two adsorptive technologies, being carbon and anion exchange resins? And so that's where we get into the treatment performance models that are going to make up the remainder of the slides. The objective here, as Sam described, is to really predict how adsorptive medias perform for removing micropollutants, specifically PFAS here. They can help interpret pilot or other testing results, as she highlighted. One of the big aspects is that if you have pilot data or other kinds of data, you can then model different concentrations, flow rates, system sizes without having to recreate that pilot. And so I think Yasmina also mentioned this, so you can leverage these models to predict out different conditions than the pilot and not necessarily have to replicate those pilot conditions. And the bottom bullet is really important. It can inform cost models and predictions, which is what a lot of people are obviously concerned with, and how to understand O&M costs and so on. So I think many people on the call may already be familiar with this, but just to orient everyone, we have this idealized breakthrough curve. This is completely hypothetical, but you have an initial period in this scenario up to about 100 days. We see that you you have significant removal. This is, depicted to about, 99% or more removal. Later in the behavior, you have, 230 days and beyond, you have no removal or complete breakthrough. And then in the middle, you have essentially the breakthrough curve that you're going to see. The width of that period or the shape of that breakthrough curve is really defined by the mass transfer zone and the development of that. And you can think about that as the kinetics or how fast the media is taking up those compounds. The capacity is another term we'll talk about in later slides. That's really setting where the midpoint of this curve is. And so if you have a higher capacity, you would move the plot sort of to the right. Lower capacity, you would be moving it to the left in sort of really high level terms. But again, you would get this sort of S-shaped curve or sometimes sigmoidal shaped curve. So this is that idealized case. Well, in reality, you get something that looks more like this. And so this is a pilot result that we published in a previous publication that I've listed later. But you don't really see that sigmoidal shaped curve. It's a flatter curve. The complexity here is that you have influent that is variable throughout time. And so you don't have a sort of fixed influent condition. And that's really what's happening in the system. So this was just, being tested alongside their normal water treatment. But the X's are the effluent data that was measured, and the black line is the model. And so you just see that it's more complex. And so the model is able to generally represent what's going on. So if we think about the basics here, in the upper left of the slides, we have sort of that capacity calculation. So there is a mathematical formula that derives that. The ion exchange model was described by Sam, where we have a selectivity. So you're actually replacing, PFAS or some other compound with the chloride, which is the common initially loaded ion on the resins. And you're basically, selecting one versus the other. The higher that K value, the more selective and therefore the higher capacity. For the GAC, we have a multi-layer isotherm. It's a nonlinear isotherm. It's the Freundlich isotherm. Here again, it's just sort of, figuring out how many nanograms of, PFAS per gram of adsorbent is going to be removed. And so that's really capturing how much sticks to the media. Below that, we have sort of a diagram of, a bead or particle of carbon. And so you have bulk flow, moving around these beads, and they will develop a boundary layer. And so the boundary layer, you have a film transfer resistance. And so that's the KL that was described. And so that's the film transfer resistance. For porous media like macroporous resins or carbons, you also have a stagnant liquid or liquid layer in the pores. And so you have a pore diffusion coefficient that would describe that mass transfer. And then you have the surface diffusion, which is, either moving through the gel type resins or along the surface of those porous media. In addition to that, we have the various colored small circles there, and that is, it's just capturing competition or fouling or other things that are happening, or the actual absorption of the compounds themselves. And so again, here, if we didn't have any mass transfer considerations, we could look at the right and we'd have that blue solid line, which would be very sharp. But we know that that's not actually happening. And so we're expecting to see that more idealized curve. That's the dashed orange line that's related to the mass transfer zone development. I'm not going to spend too much time on this other than to say that we have two different repositories to find this, and this is the next few slides. We'll go into more detail. So the first tool is part of the ET suite of softwares, which is the ADDesign S tool. This models carbon adsorption or GAC. It has a fairly simple interface. We did a training at a previous small systems workshop, and it was recorded on YouTube. And so you can see the link there, and it's about an hour and a half. It has a few inputs, so the chemical and their properties. And so it only really looks for the molecular weight, the density, and the molar volume. The duration, so how long do you want to simulate the column operation for? The column characteristics, so the length, the mass of media, the diameter, and the carbon adsorbent characteristics, so the particle size and so forth. This was recently updated to not require the license that AdDesign originally required and to be compatible with Windows 10 and 11. So the output, if you run the model, this is a TCE or trichloroethane model. It has a summary table, and it'll just automatically provide information about 5%, 50%, and 95% breakthrough. You get the breakthrough curve that we described, and then some graphing options if you want to change the units on the axes. And you can also export this to Excel if you want to plot that in your other data. You can use influent and effluent data in this tool as well to plot that as part of this. So when we started this work that Sam described, we didn't really have an ion exchange model. And so we came up with what we're calling Shiny IEX, which is part of the water treatment models repository. You can see that in the lower right, link to that. This does require RStudio, although we are looking for ways to potentially share this as a web-based tool. It does model the ion exchange process directly, as we described previously, and it models the gel type resins using the homogeneous surface diffusion model and the macroporous resins using the pore and surface diffusion model. And again, the simple interface, chemical and their properties are required for the input, the duration of the simulation, and the same kind of information that AdDesign required. And so if you're already familiar with AdDesign, you're probably going to be very comfortable with this modeling tool as well. The one difference in the output is, in addition to having the graphing options that are fairly similar, you're going to be plotting the major anion breakthrough and the PFAS breakthrough simultaneously. And so the upper plot's going to be your chloride, your sulfate, nitrate, and bicarbonate, which again are typically in a much, orders of magnitude more concentration. So we have now, these outputs can have toggleable influent and effluent data. If you have that, zoomable graphs, each chemical can be toggled on the plot. So if you have a lot of chemicals, you can see that. And in the lower plot, you may be able to see this hover information box, which will tell you the concentration for the slice there. So the dotted line hovers. And that's just another way to get information quickly. You can export this to Excel as well. And so again, just fairly nice interface. So more of the same, but we have the Shiny GAC. So in order to allow people access to some advanced data fitting capability, we created a Shiny app for the GAC process as well. It does require RStudio and Python, but similar to the other tool, we're looking at ways to make this a web tool. It will model the adsorption on carbon using the Freundlich isotherm, and it only uses the pore and surface diffusion model from AdDesign. In addition to the other capabilities, the chemical and their properties and so forth, we also include the fouling algorithms from AdDesign, so you can put in the water type and then the chemical type for including that in your simulations. So the key here is, oh, sorry about that. So we only are plotting one plot here again, but if the reddish maroon line did not line up with the data, in this case it does, but you could press the the fit data button in the lower left of the tool, and it would automatically run through and give you an estimate for what that might be for the inputs. And again, similar, it's the exact same behavior. So the zoomable graphs and so forth are also available. So again, I'm going to skip this slide, and that's just going to be the content for this next 5 or 6 slides. But the data fitting tool was demonstrated in a March 2022 paper. And this is basically looking at the, making the green line fit with the orange line with dots. And you can see on the left that there's an X, small X, which basically highlights where the best fit pair occurred. And it searched the entire space. We've sort of made advances on that. But if we take that data, so you would get parameters that would be the Freund-like isotherm parameters that made that fit, and you can use that to extrapolate these conditions. And so we actually took and modeled the case for a full-scale blended operation for the partner utility that we worked with. They were concerned with not only their current treatment rate of 19 mgd, but also their future design mgd of 44 mgd. And they also were interested in looking at, well, what happens if the concentration changes? And so on the right is the summary where we're just modeling the first change out period. So you would see a sawtooth behavior, but you can see that the different concentrations and flows through the system results in different projected change out in a blended operation. We also are looking at lead lag modeling. It's a little bit more complicated. That's the first bullet, but the last point is that the modeling tools can do this automatically, and they're really designed, set up to try to improve the O&M prediction. So if we look at the figure, if we just looked at 2 beds in series, it would say 750 days would be the projected change out. But it really is probably closer to 600 days when we consider the initial use while it's existing in the lag operation. But we also did look at homogeneous cases and heterogeneous cases, which were part of the question, and part of that was to think about short chain breakthrough. I won't go into that today, but we have looked at this somewhat, and we have the models able to talk to each other that they can understand how to do this modeling. If you're doing a lot of data modeling, you can also look at just automating this. And so this is looking at the media use rate versus empty bed contact time if you're trying to optimize that. On the left, we have an example where the influent conditions are changing. On the right, we are looking at different column configurations. And so you can just have the model set up so that these types of information can be output, and you can use that to make better decisions. One of the newer features that we've added is adding automated model uncertainty conditions. So we have the gray area that's now modeled so that the upper plots are your PFCAs and the lower plots are the PFSAs. And again, here note that the gray area generally captures the X's, which are the effluent data that was measured during the pilot. EPA also has cost models. I think this was discussed as well, but if you search EPA space WBS for work breakdown structure, or just follow the link, you can see all the available models. But there is a model for the high pressure membranes, GAC, and ion exchange as well. And so again, we can compare that to previously studied or used chemicals, and the assumptions for this plot are shown figure as well. If you are going to be interested in the models or just generally interested, there are 2 tools that are also worth looking at. The CompTox dashboard is on the left. It has 1.2 million chemicals and counting. It has a lot of lab-derived data and estimated data for chemical properties, and it has a lot of toxicological information. It's curated. It's really managed, and I think it has over something like 15,000 different PFAS at the moment, and likely growing. On the right, we have the treatability database, or TDB. This is a great resource. It's cultivated every year. It's updated, and it's peer-reviewed literature about 35 different treatment processes, and it's just a great place to start looking for information if you need that. Here are a couple papers. The paper on the left is the paper that I showed before, which is the pilot to full-scale effort. A more recent effort, Hoppert et al., is looking at the impact of phosphate and NOM on anion exchange performance with a case study partner. And so again, great resources demonstrating the models. The one on the right looks at GAC and ion exchange, but I think the interesting components there really are the impact of phosphate on the PFAS treatment performance. These are two of Sam's papers, so I'll move on from that. But this is all just what she discussed in her previous talk. One of the more recent papers as well looked at trying to predict the performance of GAC. As you all probably know, we can't analytically quantitate a lot of these chemicals, but we looked at a theoretical approach for 428 different PFAS and how likely GAC would be for economically treating that. And so the general findings are about 76 to 87% of those PFAS would likely be treatable by GAC. And we discuss the different sort of zones where the green zone is likely treatable. The yellow zone is sort of probably site specific, possibly treatable, where the red is likely not absorbably treatable with GAC. And one of the things is the general trend that we've seen in the past where higher molecular weights lead to more treatability is seen here, but we also see some vertical spread in the y-axis. So some of the compounds that have lower molecular weights are being predicted right now in this theoretical approach to be treatable. And so again, more to come if we have more data on some of these compounds. And with that, I will thank you. And the QR code takes you to the top link there, which is just all of the tools that we develop out of our group. And then the other links, just a good set of resources. And I'm happy to answer some questions.
Great, thank you, John. So yes, we do have time for a few questions before we close out today. So just kind of starting off, Jonathan, how are you calibrating your models?
Typically against pilot data. We are using some of the data that Sam described, that's the pure lab-derived data, but the underlying theory has been tested for the PSDM models, at least for GAC. These are models that have been used for decades, but we're comparing them to the pilot results and calibrating to those, or adjusting the parameters to those, rather.
Very good. So is the ad design S model just for PFAS, or can you model other contaminant removal such as DOC? And then what about the shiny IEX or shiny GAC models? If you can speak to that.
Yeah, they're theoretically, if you have the chemical data for that, but ad design has been used for years for VOCs and SOCs. But yeah, they're sort of agnostic as long as you have the parameters and the data that are required. You can use them for anything. So the anion exchange model will model an anion exchange process, and then the PSDM or the ad design and shiny GAC will model more of an organic adsorption, the Freundlich isotherm derived adsorption behavior.
Great, thank you. And then there's a few, it's this kind of a three-part question, so I'll break it up as we go here. But first off, in the early stages of design and planning, when data is very limited or experimental data is absent, would it still make sense to run a model like PDSM?
So you can, potentially use some you know, what we'll do if we don't have any data for a site, we'll usually use a fairly a fairly conservative estimate, so parameters from another site that are maybe similar TOC or otherwise. But you know, I wouldn't use it in place of a pilot or other type of data, but it could give you, you know, it can inform pilot design or other things, and we've done that in the past.
Thanks. So the second part of this question, in your uncertainty model, what factors do you consider?
That's a great question. So the plot there was showing uncertainty and capacity. We can do uncertainty in like C0 or influent concentration, flow rate, some of the mass transfer coefficients, that kind of thing. So it's all open source, so you can also add your own if you know, if you dig into the code. But those are the ones that are, you know, set up at the moment.
Great. So we'll just do a couple more questions here. So next up, alternatively, have you compared model results with data from real operating plants, full scale, to evaluate accuracy?
That's pretty limited. So we have done a few cases with fairly full scale tests. We have it was described in a previous talk about the bipartisan infrastructure law project, where we have a full scale system that has a variety of depth samples that we're hoping to get data that we can compare this to. But these, like I said, these model, like at least the PSDM for GAC model has been around for many, many years. And so it's pretty well, you know, tested.
Great. Thanks, Jonathan. And just one more question for you. For those of us that treat surface water, how sensitive are the models to water temperature?
So that's a great question, and I have not looked into that, is the big answer. You know, so the models can take temperature as an input, which varies viscosity and density, but the capacities themselves could be you know, impacted. So you probably have to understand, you know, maybe how capacity changes if you have a system that is really experiencing a wide range of temperatures. So if you have, you know, testing data from, you know, maybe a cold period and a hot period, you could bracket your, you know, models.
Well, thank you, Jonathan, and thank you to all of our presenters again today for the informative talk. We certainly appreciate it. And thank you to all of you for sticking around to the very end. Again, just a couple of reminders to please be sure to keep an eye on the Small Drinking Water webinar page. That was on the very first title slide, and which again, those slides should be attached here to the meeting today. But please monitor that for any upcoming talks, as well as any past webinars that you're interested in viewing. We do have the webinars stored there. So with that, again, just wanted to thank everyone for being here today, and to all of our presenters, and we look forward to seeing you on the next one. Thanks all.